M array communication in the presence of AWGN noise, adaptive white Gaussian noise. Here in this chapter, in this point, we have to see a representation of a random process in vector space. Just review to your last lecture, we can represent signal Si of t by using its basis function. So here Si of t, that is equal to summation over k over j, that is Si here so here Si into k, this is the coefficient. We can see that the projection of signal on kth basis function, and phi k is nothing but the basis function. So here we can see that we are having the signals, that is I is ranging from I is equal to 1 to m. So we can represent these m signals by using basis function. Here we require this capital N, which will give the number of basis function. It should be less than or equal to capital M. So we can represent all these m signals by using their basis function. So it is nothing but summation over k, Si into k, that is the projection of signal on that particular basis function into their respective basis function. And here this quantity Sik, it is nothing but integration from minus infinity to infinity Si of t into phi k of t dt. This will give the projection. So same thing we have to apply for your random process. So geometric representation of random process, write down. Here capital X of t is the random process. We can define this random process over this phi j of t, where j is 1, 2, 3 up to n. Here X of t is a random process. We can define the basis function for this random process, that is phi j of t, j is equal to 1 to n, is a complete set of orthonormal basis signal. Write down this phi j of t, j is equal to 1 to n, a complete set of orthonormal basis signals for this space. So here we can see that this X of t is given as summation of x1 into phi 1 of t plus x2 into phi 2 of t plus up to so on. We can say that xn into phi n of t. This is nothing but summation over k is equal to 1 to n, that is sk into phi k of t. Phi k of t. Here sk it given as, that is a projection of random process at k on basis function, is given as integration over minus infinity to infinity x of t into phi k of t dt. So here we are having the random process x of t. It can be represented, we can represent this random process in vector space by using basis function phi j of t, where j is equal to 1 to n up to n. So here x of t, it can be represented as x1, projection of x of t on first basis function, which will use the component x1 into phi 1 of t. Similarly, projection of random process x of t on second basis function x2 into phi 2 of t up to xn into phi n of t. So this random process can be represented using signal space analysis, geometric representation, that is summation over k is equal to 1 to n xk into phi k of t, where this phi is nothing but basis function. This sk is nothing but the coefficient. These are the coefficient which will give the projection of random process x of t on basis function. So the xk is given as integration over minus infinity to infinity x of t into phi k of t. So here we can see that k, we are in the basis function up to n, k is equal to 1 to n. So this xk is nothing but a random variable. It is a random variable which will give the value x1, x2 up to xn. So we can represent this xk by using their values. So this is a vector. Now for, it's a probability density function, joint probability density function for this random process x1, x2, x3 up to xn. It will give the joint probability density function. Is it clear? Here we are using the vector space analysis for to represent a random process. Now you are in your communication system. We have to transmit the M symbols. We will get S of t from your transmitter. At receiver, S of t plus some white Gaussian noise is going to add in your message signal. So x of t, that is equal to S of t plus n of t. Or this one we can say that this n of t, it is a totally noisy term, and this one is your random process. So here in this example we have considered x of t is any random process. Now be specific, we have to consider noise is as a random process. So write down. Now random process, consider now consider a random process as a white noise with power spectral density that is equal to n by 2. That is equal to 1 n by 2. See here we have to consider such a random process which can be represented by their power spectral density n by 2, and it is a white process. So here we can see that we will get a power spectral density for all frequencies. We will get a uniform distribution with a height of n by 2. So can we represent this white noise by using our vector space analysis? What we require to represent this random process? We have to apply the Gram-Schmidt procedure to represent this random process. What is the required thing here? We must find out the number of basis functions. So can you tell me how many basis functions are required to represent this system using signal space? And from this diagram, can you tell me what is the bandwidth of this noise? Infinite. Now you are going to represent this infinite bandwidth signal by using n basis function. Is it sufficient? Always we have to follow that Si of t, I is ranging from 1 to m, that is we are having m symbols. To represent these m symbols, we require capital N basis function. This capital N, it should be less than or equal to m. So we can represent these m symbols by using n basis function or less than m. Yes, all of you are looking towards me. So here, whatever the image is, you are looking in 3 dimension, x, y, z. But actually on paper or on board, we can represent this 3 dimension image, 3 dimension object in 2 dimension. Yes, represent 3 dimension object in 2 dimension. But in this case, we can see that we have to represent the noise, which is a white noise, which is having the power spectral density uniform with the height capital N by 2. For all frequencies, the bandwidth of this one is infinite. So represent this white noise. How many basis functions are required? Infinite. So write down, we require phi 1 of t, phi 2 of t, and so on, a complete set of orthonormal basis signal, phi 1 of t, phi 2 of t, and so on, is a complete set of orthonormal basis signal. We require infinite basis function. So we can represent this system n of t, n1 phi 1 of t plus n2 phi 2 of t, and so on. It will give summation over k nk into phi k of t. So here k is extends towards minus infinity to plus infinity, as the bandwidth of this noise is infinite. Write down, white noise has an infinite bandwidth. White noise has an infinite bandwidth, therefore dimensionality of the signal space is infinite. So here, this is the nk, is nothing but projection of white noise n of t on kth basis function. So here we will get this nk, that is equal to integration over minus infinity to infinity n of t into phi k of t dt. This nk, any component, projection of random process, white noise n of t on any basis function, kth basis function, is given as nk, that is equal to integration from minus infinity to infinity n of t phi k of t dt. So here we have to find out the relation between two random variables from your random process. So write down relation between nj and nk, relation between nj and nk. This relation is given as nj into nk bar. We are talking about two random variables. Here nj is one random variable, nk is your second random variable. So here bar is nothing but expectation of nj into nk. This is nothing but, is it a correlation? As we are finding the correlation between two random variables. Expected value of x into y. Expected value of x into y. This will give us the correlation between these two random variables. Here nj into nk, these are the two projections of random process n of t on basis function. So here nj into nk bar, that is the expected value. Here nj is given as minus infinity to infinity. Here n alpha into phi j of alpha d alpha, integration over minus infinity to infinity n of beta into phi k of beta d beta. Yes, here from this one, n of t can be represented as summation of nk, coefficient or projection of n of t on kth basis function into kth basis function. Here nk, this coefficient is calculated as integration over minus infinity to infinity n of t multiplied with phi k of t dt, that is the basis function. So here we have to find out the correlation between these two random variables nj and nk. So relation between these two, one expected value of nj into nk, that is nothing but nj can be represented as by this formula, projection of noise n of t on jth basis function, that is n of alpha into phi j of alpha d alpha. Similarly, we have to find out the projection of n of t on second basis function, that is represented by k. So this can be represented as, this projection is given as minus infinity to infinity n of beta into phi k of beta d beta. This will give the relation between these two random variables. So here this bar is representing your expectation operator. So we have to write down this one, minus infinity to infinity. Here this n of alpha and n of beta, these are the two processes. So we have to operate this expectation operator over these random processes. This phi j of alpha and phi k of beta, these are the deterministic values. Yes, we can define these values. But over this one, these two n of alpha and n of beta, these are the random processes. So we have to apply this operator n alpha into n beta bar. Expectation of n alpha into n beta into phi j of alpha, phi k of beta into d alpha d beta. Is it clear? Now see here, this is the expectation of n of alpha into n of beta. What is this quantity? It is nothing but autocorrelation function. So we have to represent this quantity as integration from minus infinity to infinity. This is the autocorrelation function over this noise, and when we consider this process is a wide sense stationary, means this autocorrelation function is the function of only distance value, that is it is a function of tau. Here this will be given as beta minus alpha into phi j of alpha into phi k of beta d alpha d beta. Is it clear? Are you getting? Now here we can see that this autocorrelation function is nothing but inverse Fourier transform of n by 2, and this n by 2 gives delta tau. So this value becomes integration over minus infinity to infinity n by 2 delta beta minus alpha and this is equal to n by 2 integration over minus infinity to infinity phi j of alpha here. This quantity, when this process is a wide sense stationary, here we have to consider that since this process is wide sense stationary, for wide sense stationary process the autocorrelation function is the function of time difference, t1 minus t2 or t2 minus t1, the difference, it is a function of difference. So here we are having the one random process at time instant alpha and second random process at time instant beta. So we have to find out the correlation between these two random processes, that is the expectation of n of alpha into n of beta, when we have to assume that this process is a wide sense stationary. When this process is wide sense stationary, we can see that their autocorrelation function Rn, definitely it is a function of this time difference, beta minus alpha or alpha minus beta, whatever. So this quantity gives me autocorrelation function Rn of beta minus alpha into this basis function phi j of alpha into phi k of beta d alpha into d beta. Now here this is the autocorrelation function, these are the basis functions, this is deterministic. As per the definition of your autocorrelation function, we can see that autocorrelation function Rn of tau, that is nothing but inverse Fourier transform of n by 2. And this n, what is this n by 2? It is nothing but power spectral density is uniform. This power spectral density is uniform for all the frequencies. They are inverse Fourier transform. In time domain, what we will get? Impulse. We will get impulse at t is equal to 0. Is it correct? So here we can represent this Rnf of beta minus alpha, this time difference, Rnf of tau, that is equal to inverse Fourier transform of n by 2, that is n by 2 into d tau, impulse function. This can be represented as impulse function. Same thing here. This autocorrelation function Rnf of beta minus alpha, it can be represented as n by 2 impulse function at beta minus alpha. Is it clear? This can be represented as n by 2 into impulse functions at beta minus alpha. So here this function is written as n by 2, one integration for this integration from minus infinity to infinity n by 2 impulse beta minus alpha. It can be represented as n by 2 integration over minus infinity to infinity basis function, that is phi j of alpha into phi k of alpha, when we will take this alpha and beta at the same instant. At the same instant d alpha, we will get this value is equal to 0 when j is not equal to k. When j is not equal to k, we have to consider the three coordinate system x, y, z. We have to find out the dot product. Mod of x into mod of y into cos of theta. This is the definition of your dot product. This product becomes 0 when x and y, they are perpendicular to each other. All of you agree? Yes or no? Here we are having the two basis function phi j and phi k. These two basis functions takes the value 0 when j is not equal to k. Means any two basis functions are perpendicular to each other when j is not equal to k. And secondly, when they are not equal, when they are equal, j is equal to k, means we are talking about only one axis, x axis, x coordinate, then it will give the value n by 2. Then it will give the value n by 2. Is it clear? In this way we have to represent this process. Here nj and nk, when they are different, they are uncorrelated to each other. You might be remember autocorrelation function, expected value of xy. We are having the two assumptions. When this is equal to 0, we can see that they are not related to each other, they are independent. So here we are having the two basis function phi j and phi k that is equal to 0 when j is not equal to k. Can I say that this nj and nk, they are perpendicular to each other? So write down, for zero mean wide sense stationary process, WSS, random process, nj and nk are uncorrelated Gaussian random variables, each with the variance capital N by 2, each with the variance capital N by 2. Here we have to assume that this is a zero mean wide sense stationary random process. So nj and nk, these are the two random variables or the random process n of t. They are zero mean, their mean value mu of nj and mu of nk, they are equal to 0. So as per the definition of your covariance of xy is given as autocorrelation of xy minus x bar into y bar. So covariance, as the mean value is equal to 0, covariance of xy is equal to autocorrelation of xy. As this process is a wide sense stationary process, so this autocorrelation function is the function of only distance or time difference, that is beta minus alpha. So here we can see that nj and nk are uncorrelated Gaussian random variables, each with the variance of n by 2. Therefore they are independent. Write down, therefore they are independent. Therefore they are independent as they are uncorrelated. As they are uncorrelated. When the random processes are uncorrelated, we can see that these two random variables are independent to each other. Here we have to prove that this phi j into phi k is equal to 0 when j is not equal to k. For all the basis functions are perpendicular to each other. Now the probability density function for this noise, write down joint probability density function. Probability density function for noise this will be given as j is equal to 1 to m 1 by root 2 pi n by 2 e raised to minus nj square divided by 2n by 2. So this will be given as 1 by pi n probability density function for this noise Similarly, we have to define jointly Gaussian random variables probability density function for jointly Gaussian random variables. This probability density function x1, x2 up to xn or x1, x2 up to xn is given as 1 by 2 pi raised to n by 2 root of determinant of k e raised to minus 1 by determinant of k summation over I summation over j delta ij xi minus xi bar and xj minus xj bar. This is covered in Gaussian random process. Joint probability density function for Gaussian random variables, that is equal to 1 by 2 pi raised to n by 2 into root of mod of k. Here k is nothing but your covariance matrix into e raised to minus 1 by 2 into mod or determinant of k summation over j and summation over I xi minus xi bar into xj minus xj bar. Here k, this matrix is given as sigma 1 1, sigma 1 2 up to sigma 1 n, sigma 2 1, sigma 2 2 up to sigma 2 n, sigma n1, sigma n2 up to sigma nn. So here sigma ij is nothing but xi minus xi bar into xj minus xj bar, and here delta ij is nothing but cofactor for element sigma ij. Here delta ij is nothing but cofactor for the element sigma ij, and when we solve this one we will get sigma ij that is equal to Rx of Ti into Tj minus so from the discussion we can see that sigma ij, this will give the k, that is sigma 1 1 variance of first, sigma 1 2 correlation between 1 and 2, sigma 2 2 that is variance of second random variable, and so on. Sigma ij, when we solve this one we will get autocorrelation function between Ti and Tj, random variables at time instant Ti and random variable at time instant Tj minus their respective mean. So to represent any Gaussian random variables or random process, only we require two things. First one, that is the autocorrelation function, and second one, their respective mean. So write down autocorrelation and means of random process are only required to define Gaussian random process. To define Gaussian random process. Now this problem for your communication system, here we have to consider M symbols. Up till now we have defined Gaussian random process. We have represent this Gaussian random process using your vector space analysis. We have to consider this noise as a random process, and we have to represent this noise process, which is a random process, using your vector analysis, vector basis function. So here we have to justify that phi j and phi k, they are 0, that is they are independent to each other. So any two random variables from this random process, they are perpendicular to each other. Now we have to define in actual communication problem. So here we have to consider m symbols with m1, m2, m3 up to mm. These are the symbols. We have to transmit these symbols. Write down. Consider capital M symbols that means we are having M1, M2, M3 up to M, capital M symbols. Here these symbols are given to transmitter. At output we will get this sk of t. Channel noise is going to add, that is n of t. Input we will get x of t, and at receiver mk of. Now here we have to transmit these m symbols. These symbols are nothing but, when we consider any continuous signal, we have to represent any point here, sample it, quantize it, or this one we have to transmit these symbols or the communication system. For this one it will give the signals. For first symbol we will get S1 of t, S2 of t signals, then S3 of t, and so on up to Sm of t. Now see here, this is the input to the receiver. One input is Sk of t. Here k is ranging from 1 to capital M. Our job is we have to represent these M symbols, M signals on signal space analysis. Its geometric representation, we require capital N basis function. This capital N, it should be less than or equal to capital M. Again, input to this receiver, here capital N of t, this is your adaptive white Gaussian noise N of t with power spectral density capital N by 2. Its power spectral density, for all the frequencies we will get the same amplitude, that is N by 2, ranging from minus infinity to infinity. So we can see that this noise is having the bandwidth infinite. So see here we are having the two situations. First one is your desired signal Sk of t, where k is ranging from 1 to capital M. These are the deterministic finite signal. We can represent this signal in your vector space analysis. We require to represent this signal, we require capital N basis function. This N is less than or equal to capital M. And in second hand, we are having the adaptive white Gaussian noise N of t, which is having the power spectral density capital N by 2, and its bandwidth is infinite. So we are trying to represent this infinite bandwidth signal on N basis function. On N basis function. See here this problem is arises. Just we have to assume that we are having the 3 coordinate system. X, Y, Z. We can represent these signals. Suppose S1, its projection on this 3 coordinate system. In this way we have to represent M signals. This is a finite quantity. Now we have to represent the n of t, which is having the infinite bandwidth. For this their representation we require infinite basis function. We are having the one object which can be represented, 3D object which can be represented by two coordinate system, x, y. Yes, we can represent. But we are having the multi-dimensional object. These dimensions are infinite. We are trying to represent this dimension, represent such an object on finite basis function. I got the problem? We are having the noise which is infinite. We have to represent this infinite noise using n basis function. Here just assume that n is equal to 3. We are trying to represent this infinite noise using this 3 basis function. Is it possible? Yes, we can represent this signal. To represent these m symbols, m signals, we are required capital N basis function. This n is less than or equal to capital M. We can represent 3D object in 2 dimensions, x, y. Yes, we can represent, but third dimension is hidden. So we have to design such a system where here for this one we have to consider that x of t, this one is given as si of t plus n of t, or this t is ranging between 0 to tm. This is the pulse duration. Either we have to use the rectangular pulse or impulse. It will use the t is ranging between 0 to tm. So in vector notation this x is given as si plus n. So here design a receiver for such a system. Design a receiver by considering vector signal space analysis. Design a receiver by considering vector signal space analysis. In first situation, write down for no noise case. For no noise case, that means only sk of t signal is present, no noise is present. So we can represent this signal where capital N is less than or equal to capital M. So we require phi 1 of t, phi 2 of t up to phi 1 of t be the orthonormal set of orthonormal basis signals for this space. So we can represent this signal sk of t, that is equal to summation or j is equal to 1 to n skj into phi j of t. Here skj is nothing but a projection of kth signal on jth basis function, and here skj, that is nothing but integration over minus infinity to infinity sk of t into phi j of t dt. Now consider white Gaussian channel noise capital N of t, which has an infinite bandwidth, capital B is equal to infinite. Therefore n of t cannot be represented, n of t cannot be represented in n dimension signal space. Are you got the problem? We are having the infinite signal n of t and we are trying to represent this n of t by using capital N dimension or capital N basis function, because this capital N by using this capital N basis function we can represent your signal as k of t, where k is 1 to m. So what is the solution? So we have to split this noise. So write down, split the noise n of t This problem is arises, we are having the three-dimensional object. We are trying to represent this three-dimensional object by using your two dimension. We have to split this three-dimensional object. That is, the portion of the object which can be represented by using two dimensions. This is the first part. And second part, the portion of the object which cannot be represented by n dimension. Just assume that we are having the x, y, z, three coordinate system. And we are in the three-dimensional object or multi-dimensional object. We are trying to represent this multi-dimensional object by using three coordinate system or two coordinate system. So here we have to consider x, y, the portion of object which can be represented by using your x, y coordinate, these two dimensions, and second part is the portion which cannot be represented by this x, y and y dimension. That is the portion which can be represented by z dimensions. Is it clear? Same way we can represent this n of t, which is a infinite bandwidth, in two portions. First one, that is which can be represented by n dimension signal space. The portion of n of t which can be represented by n dimension signal space, and this one is remaining, second part is remaining component. Write down, second part is nothing but remaining component which will be orthogonal or perpendicular to n dimension signal space. So here we are going to represent this 3D object. Generally we require the three coordinate x, y, z. We are trying to represent this 3D object in two dimensions x, y. So here we have to first consider the object which can be represented by these two coordinates x, y, and remaining part of object which is represented by this z coordinate, z dimension, and which is perpendicular to x, y. So here same way we can represent this n of t by n dimension signal space. Here we have to represent this as n I of t, this first part, n I of t, which can be represented by n dimensions, and second part, that is remaining component of this n of t, remaining component of n of t which will be perpendicular or orthogonal to the n dimensions. This remaining part is perpendicular to this n dimensions and which can be represented by n of t naught. So here we have to represent this I. This I indicates the portion of n of t which can be represented by n dimensions, or it is presented on n dimension signal space, and this portion is out of this n dimension. So this n of t, it is a summation of n of t plus n naught of t. Is it clear? So input to the system x of t, it is given as si of t plus ni of t, n of t, that is your noise, which can be given as ni of t plus n naught of t. So our job is we have to design such a receiver, optimum receiver, which will give us the minimum noise. by using your vector space analysis. In vector space analysis, we can represent the signal by using their basis function. So our job is we have to represent this x of t in signal space analysis by using their basis function. So here si of t, here we are having m symbols, m signals. So we can represent by using your Gram-Schmidt procedure. We have to find out the basis function. So for this m symbols, m signals, we will get capital N basis function which are less than or equal to capital M. Is it clear? Yes or no? Our job is we have to represent all these signals using n dimensional signal space. So we can represent this as I of t. This is a desired part which can be represented by m symbols. So to represent these m symbols in signal space analysis, we require capital N basis function. Again we are having the some noise part, n of t. So we are trying to represent this n of t using n dimensions. So we have to split this n of t, which is having the infinite bandwidth, out of which we have to select the portion of n of t which can be represented geometrically by using capital N dimensions. So out of which we have to consider this n I of t, it can be represented by capital N basis function. This is the first part. And secondly, the remaining part which cannot be represented by capital N basis function. This is out of the scope. This one is out of the scope. Is it clear up till now?